So I have two small topics, composition of extensions, compositum. And I want to talk a little bit about embeddings of fields. So here's the first one. Suppose you have a field extension k over f. You have two intermediate fields k1 and k2. Then one way to build a new extension is to take the smallest subextension of k over f that contains both k1 and k2. This thing is denoted by k1, k2. So it's the smallest subfield of k that contains both k1 and k2, and it's called the compositum of k1 and k2. But given extensions k containing k1, k2, both containing f, let k1 times k2 denote the smallest subfield of k containing both k1 and k2. It's called the compositum k1 and k2. So example, if you have k over f and you take two elements in k, you can add them one at a time and you get some subextension. If you take the compositum, that's same as if you added both of them. Yeah. So this is the smallest subfield of k that contains both this guy and that guy. So example of example, like you take, this is a huge extension, you take two numbers, you can add them one at a time, then you get these two degree 2 extensions, or you could add both of them. That would be the compositum of q root 2 and q root 3. So maybe you can prove by hand that sometimes, so you see the way this is described, this is obtained by adding two numbers. It turns out you can just get by adding one thing. In fact, this is true for any finite extension of q. You can get by adding just one element, but that will require some proving. But here you can check that by hand. Of course, root 2 plus root 3 is contained in q root 2 comma root 3, so this containment is clear. For the other one, you have to show that both root 2 and root 3 are here. So I guess the easiest way to just directly see that in this case is if you take the reciprocal of this, that's same as but the denominator is just 3 minus 2, but root 3 square minus root 2 square, which is just 1. So this is just root 3 minus root 2. Yeah. So because this field, let's call it k contains root 2 plus root 3, so it contains its inverse. So this is also in k. So now that we know root 2 plus root 3 and root 3 minus root 2 is there, so then if you add them, that's 2 root 3. That's also in k. But then 2 is in k, so root 3 is in k. And once you know root 3 is in k, you know root 2 is also in k. So they get the other inclusion. And one other exercise before we move on, maybe in general, you can show that if both these are finite extensions, k1 and k2, then the compositum is also finite. In fact, the degree of the compositum is less than or equal to the product of the degrees. And this would be a good exercise to do actually. If you take a basis of this over f and a basis of this over f, out of that you can cook up a spanning set for k1, k2 over f, I believe. Something like that. So here in the example that we just did, for example, this is a degree 2 extension, this is a degree 2 extension. You can show rather easily that root 3 is not in here. So this here is a proper extension, meaning these two fields are not the same because root 3 is in this field but not in that field. Okay. So once you know that this extension from q root 2 to q root 2 comma root 3 is also degree at least 2. So now you know that this extension is degree 2, this extension is at least degree 2. So the big extension is degree at least 4 because the degree multiplies, remember? On the other hand, we just checked that q root 2 comma root 3 is equal to q root 2 plus root 3, and we also showed that this satisfies a degree 4 equation over q. This we checked sometime before. So that tells you that this degree is at most 4. Now that you know that it's at least 4, it's at most 4, then it's 4. So this is actually of degree 2. This is also equal to degree 2. And this is a degree 4 extension. These are called biquadratic extensions, adding 2 square roots. If you add, and in these cases they're degree 4. Or you could actually quote this exercise if you have done that. This exercise also tells you that because this one is degree 2, this one is degree 2, the compositum is degree at most 4. But then you can check that it's at least 4 because the bottom part is at least 2 and the top part is also at least 2. So that would be another way of arguing it. So the other thing I want to talk about a little bit is embeddings. A different topic. So it's basically a remark I wanted to make. You see, I mean, when we were doing ring theory, we were talking about ring homomorphisms a lot. When we were doing group theory, we were talking about group homomorphisms a lot. And they were sort of the central focus. So here we have been basically talking about one field contained in another field, rather than, so it's basically we're talking about these inclusion maps. Another way to say that. And the point is that non-zero field homomorphisms are always injective. So the remark, the first remark or first observation, if is a non-zero ring homomorphism from and f and k are fields, then f is injective. Because the kernel is an ideal, but a field doesn't have any ideal. The only ideal, any proper ideal, is the only ideal is 0, since the only ideals in f are, since only ideals in f are just the 0 ideal and f itself. So if it's a non-zero map, then the kernel is not the whole thing, so the kernel has to be just 0, which means that the map is injective. So this allows you, so f is actually isomorphic to a subfield, namely the image of K. So the study of a non-zero homomorphism basically becomes study of f sitting inside K, because you can often, when you have this sort of situation, now you have f isomorphic to its image, which is sitting inside K. So you can often identify this F with that image and think of F as a subset of K. And then this, you really are studying one field sitting in another. At any rate, because of this, injective homomorphisms often come up, and we'll see once we study splitting fields and stuff, and separability, this becomes a key notion, looking at these injective homomorphisms. So they have a name. An injective homomorphism of fields is called an embedding. Injective homomorphism of fields is called an embedding of fields. Because there, when you have an injective homomorphism, you are not collapsing anything. So basically the field that you are embedding, this guy sits inside that guy. Yeah. And oftentimes we will be addressing this question, that you have an embedding, let's say, sigma from one field to another. We'll denote it like this because it's an injective map. We put a little hook. And suppose I have an extension. So it's a bigger field. We will often ask, when can I find an embedding here from K to L which restricts to my sigma? So we'll make a definition and we'll see why this is relevant next time. So let sigma be an embedding and K over F is an extension. Say that sigma extends to K. That's the new word. If there exists an embedding sigma prime maybe from K to L such that its restriction to F is your old sigma. So example would be like if you take that's an extension of Q. This is the extension obtained by adding a square root of 2 abstractly. You have Q sitting in R. Can I extend? Yes, I can. How can I extend? I can extend it by sending this. Remember we had this alpha here, the image of x. P is x squared minus 2. If you can send alpha to a square root of 2, either root 2 or minus root 2, that would be an extension. You can check. So these extensions correspond to the roots of this polynomial that are available in this bigger field. And this will play a big role when we get to Galois theory. Okay, next, we are ready to talk about splitting fields.